Hi everyone, thanks for coming to my talk about using machine learning to understand our society. I'm very excited about this research I've been doing, and in this talk I'm going to explain exactly what I'm doing and why it's so cool. So I've set up a nice mailing list for updates. If you'd like to get updates about what kind of progress I'm making with the research, please sign up and you're going to get an update maybe once a month. This is going to be a talk about machine learning, but you don't need any kind of background in machine learning to enjoy it. I've packed a lot of material into this talk. There are 66 slides in 45 minutes, so there won't be any time for questions. This talk is oversimplified, right? The objective is to be interesting and to have you understand pretty much what's going on. So not everything I'm gonna say is 100% accurate. This is going to be a talk about my research, but I'm going to spend maybe 10% of it talking about my actual research. I'm going to spend most of the talk defining the problem and talking about existing research by other people. I'm going to show a bunch of videos and demos. It's going to be a lot of fun. So here's what I'm going to talk about. I'll talk about my personal story. I'll talk about the big picture of what I'm trying to achieve with the research. I'll give you a crash course in multi-agent reinforcement learning, which is the field in which I'm doing the research. I'll talk about what I've done in practice and what I'm going to do. And then I talk about the great challenge of cooperation. So this is me. My name is Ram. Many people know me as an open source activist and Python developer. I've, I've developed a couple of popular open source projects called PySnooper and Python Turtle. And I've also contributed to lots of existing projects, CPython, Django, and PyPy. And I'm a fellow of the PSF. So I'm going to tell you a bit about my background. So I'm a software engineer, and I made a very different track than most other engineers. I don't have a university degree. Ever since I was young, I had a very great resistance to being part of the system, but part of the establishment. When I was in my early 20s and I was studying, I used to show up at university and just come to classes and learn and even do the homework, but I didn't enroll in university. I was very, I had a great resistance to that. I wanted to do things on my own and decide how I'm doing things. So this is something I've dealt with my entire life, and slowly now I'm 36, and over the years I've become more, I've conformed more to society, and now I'm okay with being part of the system. But it was a very difficult process for me. So I've been working as a developer for 12 years. At first, I was a freelancer. I was working for small startups. I mean, I was the kind of guy who writes the first line of code of the company and develops, like takes an idea and develops it into a product. I was comfortable working alone on my own passion projects, but it was very difficult for me to work as part of a team and part of a company. So it took me, I mean, I started working in big companies 6 years ago. It was a very difficult learning process. I mean, I've gotten better at it, but it was difficult and very insightful. I mean, I would say it was almost a spiritual experience. And this sort of conflict between the individual and the group is something we're going to talk a lot about regarding the research. So let's talk about the big picture, what I'm trying to achieve with the research. So I want to use machine learning to answer big questions about human culture. So obviously, I say like that sounds so big. Let's start with something small that makes it easier to understand. So this is a computer game Mario. And this is an AI agent playing Mario. And the interesting thing here is that this AI was not taught the rules of the game Mario. It basically, they hooked up this AI to a Mario system, hooked it up to the video output and to the output of how many points Mario has and how many lives he has and how many levels he's gone through, and basically told the AI to maximize these metrics. The AI does a sort of trial and error to understand how to get as many points as possible, or die as few times as possible. And at the beginning, the AI just moves randomly around the screen, just doing random stuff, mashing the keys together without understanding what's going on. But after like playing 100,000 hours or something like that, it slowly becomes more adept at doing tasks like right now jumping on these monsters and killing them. And I really love this. I really love this demo. I mean, this isn't very new technology. It's around 10 years old. And in this talk, we're going to see research that's 50 years old and research that's 2 weeks old. But this demo really hits different for me because we've seen a bunch of crazy AI demos these last few years. We've seen the ones where the AI makes a face of a person that doesn't exist. And we've seen the GPT-3 and Lambda having conversations in text that feel like a human being is actually having a conversation with you, and these are very impressive. But this demo really is really, I like it a lot. I mean, what I like about it is that Mario is out there, shooting his shot, and walking around the world, trying to, stay out of trouble and get as many coins as possible and survive. And he's making decisions and dealing with the consequences of these decisions, which is a lot like life. So the fact that the AI was able to figure that out, and the AI is walking around the world and on a world that is new to it, and trying things and seeing what works, that for me is very close to the human experience. So this is something that I would like to take and say, how can I make this even closer to the human experience? And I think the biggest thing missing here, I mean, if I had to say what is the biggest gap between this Mario demo and the human experience, is that there is no cooperation. I mean, it would have been cool if Mario would have met other Marios or other people. I mean, right now Mario is meeting monsters, and he has a fight or flight response to them, which is a good start, right? It's really interesting to see Mario sometimes running away from monsters and sometimes killing them. But it would have been even nicer to see if he was collaborating with them in some way, like making friends with them and doing something together. That would have been awesome. And this is the research paper related to this example. Throughout this talk, I'm going to show a bunch of different research papers, and I'm going to also have the link on each one so you could go ahead and read them to get a more in-depth understanding. So I am most interested in seeing relationships and groups. I mean, I want to see AI agents that behave kind of like people, and I want to see them make relationships and get in groups, and I want to see the social dynamics in those groups. And now I want to show you a video that does go into that direction. This is going to be a video by OpenAI. So let's just talk about the big three in the world of corporate AI research. And I hope no one gets angry at me about this, because maybe I'm forgetting one of the major accomplishments or one of the major players. I'm sorry. But anyway, you've got the Google Brain, Google AI, Google Research, and DeepMind with their protein folding and AlphaGo and TensorFlow. And you've got OpenAI with GPT-3 and the others. And you got Facebook AI Research. And we're going to see a really awesome video by OpenAI, and it might be the best video I've seen on the subject of multi-agent reinforcement learning. So let's give it a watch.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play.
Okay, this was a great video, and I want us to notice a bunch of cool things about it. Number one thing, which obviously cool, is the way that the agents cooperate, right? We've got a team of hiders and a team of seekers, and each of these teams within their own team, they cooperate to beat the other team. So that's exactly what I want to see. And another really important thing is the way that the levels of learning are stacked up on top of each other. Um, the hiders learn how to build a shelter, and then the seekers learn how to break into that shelter by using the ramp. And then the hiders learn how to hide the ramp. So I've now spoken about three levels of learning: building a shelter, using the ramp to penetrate the shelter, hiding the ramp. And each of these learnings was based on the previous one. So each layer, these layers of learning are stacked up on top of each other in a way that's very similar to human culture. This phenomenon is called autocurricula. That's the big word you see in the title of that research there. And in my opinion, it's one of the most important concepts in the world of reinforcement learning. Another thing to notice before we continue is that the genre of this game was different than Mario. I mean, we no longer had coins and turtles, and we now had ramps and boxes. And in this talk and in my research, I don't really care about the genre of the game. I only care about the way that the agents behave and how they treat each other. Now, and the biggest thing I want to note about this video is that, in my opinion, there is something missing in the social dynamics between the agents. Something in the way that the agents behave is a bit off, and this is something that I would like to improve. So I'm going to tease you with that. I'm going to tell you the answer only after the next section, which is a crash course in multi-agent reinforcement learning. So I'm going to teach you the basics of this field. Let's first talk about reinforcement learning. So reinforcement learning is machine learning applied to game theory. So game theory is a field of mathematics that studies having the concept of having a situation in which you make a bunch of choices. In which you make a choice out of a bunch of choices, and you choose an action to do, and that action leads you to a new situation in which you're going to have a new array of actions to choose from, and then you're going to choose another action. You're going to get into new situations. Some of these situations are good for you, and some are bad. So game theory is applicable in economics, in lots of other fields, and obviously it's applicable to game, like chess or StarCraft or any other kind of game. And reinforcement learning basically says, let's take the all the nice machinery of machine learning, the neural networks and stuff, and apply them to game theory, which means apply them to a situation in which you have to make a choice. So use machine learning, use that neural network to figure out what is the best choice to take. Um, Reinforcement learning is naturally applicable to games. This is a part of the movie AlphaGo. It's a documentary. You can find it on YouTube. I recommend watching it. It's a documentary about the AlphaGo project by DeepMind. So you probably remember that 20 years ago, there was a big deal when the IBM developed an AI that beat Kasparov, the world champion at chess. So this is sort of the modern version of that. Go is a more complex board game than chess, and DeepMind has managed to create an AI that can beat the world champion Lee Sedol at Go. So, very big accomplishment, a cultural achievement. But the reinforcement learning is applicable not only to games, but also to real world problems that can be phrased as games. When I say phrased as games, basically, if you can take a real world problem and phrase it as a situation in which you have to make a choice, and that choice leads you to another situation in which you have to make another choice, then you can apply reinforcement learning to it. This is a research paper from a few weeks ago, where the researchers at DeepMind took the code from AlphaGo and used it to improve YouTube's compression by 4%. So hugely impactful achievement. Let's talk a bit more about reinforcement learning, and let's compare it with a more well-known type of machine learning, which is called supervised learning. So let's take this example. Let's say I got my phone, and I'm using the Google Lens on my phone. I'm taking a picture of my computer monitor, and the Google Lens is giving me the link to that model of monitor, and it's so I could buy another one of these monitors. So in this case, the machine learning system got the input, which is the picture of the monitor, fed that into the neural network, and produced the output, which is the link to buy it. And it was a one-shot interaction, as many machine learning interactions are. In reinforcement learning, there is sort of loop because the input to the system is the state of the game, the state of the world. Right? If this was chess, then the input would be the positions of all units on the board and whose turn is it, and information like that. And then the neural network makes a decision on what to play, in this case, moving the knight to a4, and the output is that move. And unlike the supervised learning example, the output is then fed into the environment. Now, the environment, in this case of chess, basically means that you make the move on the board, and the black player, whether it's a human player or an AI player, makes their move, and then their move becomes the new input, it becomes the new state of the game. And then our system makes a new decision with the neural network, and round it goes. So with reinforcement learning, the system doesn't only make decisions, it's also dealing with the consequences of these decisions, which is a lot like life. Another classic example of reinforcement learning is self-driving cars. Self-driving car is an agent that's out there on the road, and it's in a situation on the road with cars in different positions. And at every point, it is making a decision: am I going to go forward? Am I going to go backward? Am I going to turn right? Am I going to turn left? Am I going to go fast? Am I going to go slow? And each decision leads it to a new situation. It's going to be in a new position in the road, and then it's going to have to make a new decision about whether to turn right or left. And in the world of supervised learning, like the example I gave with the Google Lens, there is a very objective definition of what is a correct decision. Like this, I took a picture of the computer monitor, and the system gave me a link. The Google Lens gave me a link to buy that monitor, and the link might be correct or it might be incorrect, and there might be a bunch of incorrect or a bunch of correct links and an infinite number of incorrect links. But this definition that the output may be correct or not correct doesn't exist in reinforcement learning. Because in reinforcement learning, we don't say what the answer that we want is. We say what the sort of general result that we want is, and we trust the reinforcement learning system to kind of find the way towards that. Um, for example, let's talk about the self-driving cars. Let's say I'm using my self-driving car, which I don't really have, to get from the office to my apartment. Then I want to get from the office to my apartment as quickly as possible, and I don't want to get into a car accident, obviously, and I don't want the ride to be too bumpy. These are sort of my goals for the system, but I don't tell it what to do at every step, right? And the system makes a decision. Let's say the car arrives at the junction. It has to decide whether to turn right or turn left. And say that he does turn right, and he does get me home safely. The system can't know for sure whether the decision to turn right was correct. It's possible that if the car turned left instead of right, it would have gotten home faster. It also could have gotten home slower. It also could have gotten into a car accident. So it's very difficult out of the thousands of decisions that the system makes from start to end. It's very difficult to say which of these were good and which were bad, and there isn't even an objective criteria in which you can say if they were correct or incorrect. You can just kind of get an opinion of whether they were good or bad. You can try to use that opinion to make better decisions next time, but there isn't really an objective way to say it was correct. This is very difficult. This makes reinforcement learning so difficult, but it also makes the potential so much bigger because this kind of dilemma where we don't know which of the choices that we made are good or bad, this is very similar to our own lives. So there's an opportunity here for AI to get closer to the actual lives that we have as humans. So far, we're talking a lot about the ways that reinforcement learning is more difficult and challenging than normal machine learning. Here is one way in which it is easier. Training data. Getting training data is a chore. Again, with the example of the Google Lens, and I said that I can use the Google Lens to take a picture of my monitor and I would get a link to buy that monitor. This means that the system, the Google Lens, was fed millions of pictures of different monitors, different office chairs, and different desks, and different all kinds of products. And for each of these pictures, it was fed the link that is appropriate for that picture. And the neural network was trained to give the correct output with the correct input. Now, collecting that training data and curating it, making it available and accurate, that is such a chore for researchers. Also, eh, I mean, also it brings up all kinds of problems of legal problems of using what happens if you use other person's training data, stuff like that. So that's a huge obstacle. And in the world of Reinforcement learning, the training data is basically just game history. If I want to train my RL agent to play chess, I just have to give it millions of games of chess. Each of them has 50 or 100 moves, and on every move it can see which move led to which other move and which move led to victory, and then it can use that data to learn to become better. And the beautiful thing here is that we can just produce that data. I mean, I can have an AI that plays chess, even if it plays very badly. I can tell it, just play a million games of chess against yourself on the computer. Bam! I don't need anything. I just got a million games of chess, and I can use that as training data. And it might not be the most high quality, but I can use that. But I can use that to make the agent just a little bit better at chess, and then I tell it to play another million games against itself, and this data will be of a higher quality because now it's a better player, and that way I can make the gameplay. I can make the AI agent better and better, and I can produce the training data only by training the CPU without having to do any kind of action in the outside world. So that is a really nice thing about reinforcement learning. And again, we have here sort of an example of an autocurricula, because when I produce the first batch of data, the first million games with that AI that barely knows how to play chess, it moves randomly. The the structure of the training data was of a poor quality, and that quality, it can improve the performance of the AI agent to produce games that are played better. So the character of the gameplay of that AI agent is going to always be affected by the training data that it has. It's going to change as the agent learns and produces better data. So I said that the big challenge is the fact that system make 100 decisions or 1,000 decisions, and it's so difficult to figure out which of these were good decisions and which were bad. And the algorithm to figure that out is called temporal difference learning. So obviously, I'm not going to go into that here, but I recommend that you read the book Reinforcement Learning: An Introduction by Barton and Sutton if you'd like to go deeper into that. So far, I've spoken about reinforcement learning as a single agent. Single agent basically means that we have one agent, like a chess player or a self-driving car, that sort of makes decisions. But in the real world, we have to deal with multiple agents. Self-driving car is a great example. Self-driving car is riding around on the road, and on the road there are lots of other cars, some of which are self-driving cars and some of which are driven by humans. And the self-driving cars could be of different companies. And our car has to somehow survive in that world. It has to sort of understand what the other cars are doing. It has to communicate, like using the turn signals, to get the other cars to understand it. So this study of the way that different agents interact, that's called multi-agent reinforcement learning. And in my opinion, it is, I mean, that is a fascinating field. And reinforcement learning by itself is mainstream, it is prestigious and considered a very interesting field of study. But within reinforcement learning, most of the focus of the research has been on single agent reinforcement learning. I would say around the 90%, with only 10% dedicated to the multi-agent reinforcement learning. Now, I would like to change that. I would like to show the potential of multi-agent reinforcement learning. So I've given you a crash course in multi-agent reinforcement learning. And now let's talk about my research in practice. And I've teased you earlier about the hide and seek video. I've shown you that video. I've said how awesome it is, but there is something missing in the social interaction between the agents. And their their cooperation was very impressive. They were beautifully coordinated. And what I'm claiming here is that their cooperation was too good. Why was it too good? Because they were compensated based on the success or failure of their team. We had a team of seekers playing against a team of hiders. Let's say that there were three seekers and three hiders. If a single seeker, one of the three seekers, found one of the three hiders, then the entire seeker team would win, and each of them would get 10 points, where the entire team of hiders would lose, and they would each lose 10 points. And there was no element here of, hey, I worked my ass off to find the hider. Why am I getting the same points as you? Well, you didn't find any hider at all. There was no conflict between the individual and the group. But I do want to have that conflict. I mean, I want the agents to cooperate, but I still want them to be individuals. I want them to still have a sort of a individual experience that leads them into cooperation. And I don't want that cooperation to be perfect. I want them to be imperfect. I also want them to be able to decide which team they're on, because in that hide and seek research, we've had two teams, and this team size was constant. And for each agent, we defined in advance which team they're going to be in. And that's not how life works. I want individuals that work in teams because they decided to work in a team, because they built the team. And I want the teams to sometimes, get bigger, get smaller as time goes on. I want a more authentic experience. Now, many researchers have been trying to do that, and they weren't quite successful. And as soon as the agents are given are allowed to be individuals within a society with other agents, they quickly become the most terrible people they can be. Now, there are some research papers that get imagined cooperation, but they make assumptions that are too big for me, or they have asterisks that are too big for me. So let's see a very instructive example. This is a game in which the player needs to eat as many apples as possible. And the apples grow on two trees. And the catch here is that if the player eats all of the apples of a given tree, that tree dies and doesn't produce any more apples. Now, this player has played many rounds of the game, and now it's playing it in a very good strategy because it is eating the apples, but not all of the apples, and it's rotating between the two trees. And every time it's eating apples on one tree and letting the apples on the other tree grow and repeat. And this way, it's able to eat an infinite number of apples. So this is good. Now let's see what happens when we unleash multiple agents on multiple trees. The agents immediately kill all the trees, and now they are wandering aimlessly around the world looking for apples that no longer exist. This with this behavior, we know this behavior from real life, right? People behave like that, and that is something that is very frustrating to us, and it's something that as a society we think a lot about. I can say global warming, and I can say saving the environment, and I can say so many different scenarios in which people behave that way. And when we see that people behave that way, we sometimes think, that's just how it is, or that's just how people are, or that's just how these people over there are. We would never do something like that. And the really enticing thing about multi-agent reinforcement learning is that now we can see this frustration as a mathematical phenomenon. Because we know for sure that these agents that have just ravished their environment, they have the exact same brain, the exact same neural network as the one agent that did conserve its environment. And we can pinpoint the difference to the social dynamics between the agents. So finally, instead of being bitter about this problem, instead of growing hateful about the way people behave, we can see the problem as a mathematical problem, and we can find a mathematical solution. We can we can try to come up with a situation in which the agents do cooperate and figure out what are the main differences between these situations and the tragic situations like this one. We can sort of find a mathematical definition of the requirements for cooperation. We can study and understand the way that selfish agents cooperate and use that to understand how people can cooperate better. Now, this is why I'm so excited about my research. I think there is an amazing opportunity here to discover something that is so essential to the human experience and has the potential to improve the world in incredible ways. This is the paper from DeepMind that I took the two videos from. The second author here, Edgar, is my mentor in my research. Now it's time to talk about my long-term research goals. This is like maybe looking for 20 years, right? This is very big, and you don't have to read the whole thing. But basically, I want to create a world, which basically means invent a game with game rules that has these RL agents. And I want them to start as completely selfish, and I want them to cooperate, but not perfectly. I want them to still be individuals, even though they cooperate. And sometimes I want the cooperation to fail. I want them to fight. I want to see them form up groups, and I want the groups to also sometimes break up. And I want agents to join groups and leave groups. And I want to see sort of human-like drama. Now, I want to use these experiments for two goals. A, I want to get a better understanding of human society and how we cooperate. And B, I think this might be a good stepping stone towards artificial general intelligence. I think it's possible that a collection of multiple agents acting as individuals but forming a group, it's possible that these agents could do things that are useful to us, that a single agent, however smart, can't. Okay, so here's a timeline of some of the work I've done. I first became interested in this field back in '06. I was telling you before that when I was in my early 20s, I didn't get a university degree, but I did show up at university and I just came to different courses and learned on my own and did the homework, stuff like that. So that was in the Hebrew University in Jerusalem. So back when I did that, I saw there was, I mean, one day I was walking around the campus and I saw there was an ad for a course by Robert Oman on repeating games. Repeating games is a field of game theory, and Robert Oman a Nobel Prize winning professor who got his Nobel Prize for his work in repeating games. So I thought I have a chance to learn from the master here. That's awesome. Let's do that. I attended the course, and when he taught about iterated prisoner's dilemma, it really opened my mind to the kind of possibilities that this field has. I never thought I would be working on it full time, so I'm really happy that things turned out that way. Over the years, I ran a couple of experiments, but not really seriously. And in 2020, I began to really take um, this research more seriously, and I ran a bunch of experiments I'm going to show later. But starting in January 2021, I met Edgar, and he has been my mentor. And now really feel like the research is sort of like the main thing that I'm doing. And now I really feel like there is potential for me to write a research paper that is going to really innovate and make a breakthrough in the field. So Edgar is basically doing the same thing I'm doing, but for real. Edgar is a research engineer at DeepMind. Uh, uh, he works on the multi-agent reinforcement learning team, and he's written a lot of papers on the sort of intersection of multi-agent and social behavior and biology. And he's especially interested in using AI to fight discrimination. And he's got this I have to say paper about it here. Let me oversimplify. Basically, he's got a group of red agents and a group of blue agents, and every agent needs to pick a friend, and he's incentivizing the red agents to only want to be friends with other red agents. And after he's incentivized them for that, he removes the incentives and see whether he can wean them off their discriminatory behavior. Right? So trying to get a conclusion from that to how we can fight racism or discrimination in the real world. So very, very interesting stuff. So I approached Edgar and I had zero academic experience, right? I'm experienced as a software developer. I mean, I can write, I'm into open source, I can present, but I had zero academic experience and didn't even know how to read research papers. So Edgar had to teach me that. So I talked with Edgar and I shared my plan, my research plan. He was excited because it's similar to his. He sent me a bunch of papers to read. I read them. I had questions. We met every 2 weeks, and he kept sending me more papers. And we've done a bunch of iterations like that until I got to the point where I know what's known in the field and what the open questions are. And we use this information to plan an MVP. I say an MVP because at first I have to sort of prove that I'm making good progress, that I'm making some kind of contribution before I can continue with my ambitious research plan. So here's my MVP, a more simpler version of my long-term research goals. I want to create a world with multiple RL agents, and I want the agents to start as selfish, and I want them to cooperate in some way. I mean, I want the agent to, in some way, take a risk for other agents or trust other agents. If this works, and I can show that I've gotten this emergent cooperation, that would be a nice paper, and that I could co-write with Edgar, and I could continue on my bigger goals. And depending on how strong the evidence will be in my research, this could be a revolution in the field. And so let's talk about that now. Let's talk about the great challenge that is cooperation. I've shown you the videos with the trees before, and I've sort of demonstrated why cooperation is so hard to get. I mean, it's so difficult to get these agents to understand that they need to be good to each other. And the key to getting there is reciprocation. So we've shown that game with the trees, and we've shown a bunch of different games. We've shown Mario with the coins and turtles. We've shown hide and seek with the ramps and boxes. But I really want to focus on the cooperation bit right now. So I want to remove all of these elements from the game, all of the game mechanics, just no trees, no ramps. I don't even want a physical space. I just want every player to have to make one out of two choices. Am I going to be nice or am I going to be mean? And this game is the most famous game in game theory, and that's called Prisoner's Dilemma. And there are only two moves: cooperate and defect. Cooperate means be nice, and defect means be mean. If both agents cooperate, if they're both nice, they both get a reward. But if one of them is nice and the other is mean, then the mean one gets a lot of points, while the nice one loses a lot of points. And the interesting thing about Prisoner's Dilemma is that it really shows you that the tragedy doesn't come from a place of evil, because each of the two agents in this game is afraid that the other one is going to be mean and going to win lots of points, and that our agent is going to lose lots of points. So each one of them sort of acts mean defensively. Each one of them defects because even though they're going to both lose points for defecting, at least they won't lose a lot of points. So this is the tragedy, but it's also nice to see that it doesn't come from a place of evil or ill intent. Here's a simulation of players playing Prisoner's Dilemma, with the blue players are cooperating and the red players are defecting. And as soon as the red players get hold of the population, just everybody goes and defects. Because there is no defense when someone is defecting against you. There is really no defense except if you can't beat them, join them. And Prisoner's Dilemma gets interesting once you play multiple rounds of it. Let's say you're playing 10 rounds of Prisoner's Dilemma against someone. You're gaining points, losing points. Suddenly, because you're playing multiple rounds, there suddenly, if you are defecting, there might be repercussions for that, because you're going to play more rounds. If you're going to defect on someone, they might defect back on the next round, and then maybe you might think twice before defecting. This behavior is called reciprocation, and it is the basis of cooperation. And here's the simplest possible strategy that implements reciprocation. When you play, let's say, 20 rounds of Prisoner's Dilemma against someone, very first round, you play cooperate. And then on every subsequent round, you play the same move that your opponent played on the previous round. So if you meet a cooperator, if you meet an agent that always cooperates, you're always going to cooperate back. And if you meet an agent that always defects, you're always going to defect back. And this behavior makes it unprofitable for agents to defect against tit for tat. Tit for tat is, you could say, it's the hello world of reciprocation, the simplest possible example that works. The really interesting thing here is that because it is cooperating, it's cooperating, but it's never left holding the bag, and that's something that can make cooperation stick. And I'm going to show you a demo of that later. Now we want the RL agents to learn tit for tat, to learn any kind of reciprocation, but they just don't get it. This is a nice demo that you can see on reinforce on on Prisoner's Dilemma, a very interesting interactive demo. So I was saying we want to teach the RL agents to do tit for tat or any kind of reciprocation, but they don't get it, and I'm going to show you why. Let's say that we have a world with lots of different agents, and none of them have learned cooperation or reciprocation. And we've got this agent right here, and it learns suddenly gets the bright idea to try tit for tat or to try something like tit for tat. And it's playing with all of its neighbors, and now it's saying, "Hey, I'm going to cooperate with all of my neighbors for once. Let's see, let's see whether that can get the ball rolling." But these four agents around it, they don't know tit for tat. So they don't, when they see this player cooperating, they think, "Oh, awesome, I just got a bunch of points. I defected and I got a bunch of points. This is awesome. Let's keep doing that." And this agent is just going to lose lots of points, and it's not going to get anything back for its cooperation. And I said that these agents learn with trial and error. So if they try something and it doesn't work, they just don't try it again. They just try what works. So this agent now tried something like it for that and lost a lot of points, and it's basically concluding, "I'm not going to do that ever again. That sucks." And each one of these agents is in the same kind of dilemma, because if any of them tries to do something like it for that, it wouldn't be appreciated by its neighbors. So there is real tragedy here, because there is no ill intent or evil on behalf of any of these players, but they will never be able to learn tit for tat, because tit for tat makes sense only when other people already know tit for tat, right? So there is a sort of catch 22 here, because how can you learn tit for tat where nobody around you knows tit for tat? Then the big question here is, how can we jumpstart this phenomenon? And let's talk a little bit about cooperation in our daily lives, because I've said the word cooperation like I've said it like 100 times by now, and we've spoken about cooperation in the world of these agents. And but when I say cooperation, I mean in our daily lives, you might think of something like teamwork. You might think like, hey, I'm part of a team at work. I've got projects I'm working on with my team, and I will say, hey, I'm going to do this, you're going to do that. I'm going to help you with this. You're going to ask me questions about that, and we help each other. That's cooperation, and that is true. But we are humans, and we are such evolved creatures, and we have so many layers of cooperation stacked up on top of each other that we take the lower levels for granted. I mean, just the fact, I mean, put teamwork aside, just the fact that when I speak to another person, then they are able to not speak when I speak, they stay silent, and I talk and they listen to what I'm saying. And then when I finish speaking, they start speaking, and then I shut up and listen to them. Just that basic kind of coordination is something that is challenging for these agents. Just the fact that I can hold eye contact or shake hands with another person, that is cooperation that is very challenging for these RL agents. Now, when we're angry and hurt other people on purpose, that is also cooperation. Let's give an example. Let's say I'm walking down the street and I accidentally brush against someone, and that someone is in a bad mood, and he's staring to me and says, "Don't touch me, or I'm going to kick your ass." Even though this behavior is aggressive and hostile, it is a kind of cooperation because that person is saying, "Listen here, we've got rules on how we behave. You did something that is not legitimate, and I'm going to punish you for that, or I'm going to threaten to punish you because I only want people to act in a way that abides to the social norms." So even though it is negative feedback rather than positive feedback, it's still feedback that reinforces a social norm. And the last kind of cooperation we don't think about is the cells in our body. We are multicellular organisms. We are built of millions of cells. And each of one of these cells that make up our body is a living creature on its own right. And these living creatures used to look like the one on the left, which is a single-celled organism. Now, this single-celled organism uh, walks around, I mean, moves around the world trying to survive, trying to find food and replicate and stay out of trouble. While these agents on the right, these cells on the right, they are living creatures, but they only deal with the neighbors that are next to them. And all of them together, the millions of them as a collective, they worry about the success, the survival, and reproduction of the collective. But each of these cells don't need to deal with the outside world. And we know that the kind of structure on the right comes from the kind of structure on the left, but we don't know how. Now let's talk about what science knows about cooperation and what isn't known. Now, again, we have the selfish agent on the left and the cooperating agent on the right. And the science feels very comfortable with the selfish agent. And we see that in many facets. I mean, for example, in our economical theories, I think capitalism feels very comfortable with the fact that every person wants to have as much money as possible, and every company wants to have as much profits as possible. And we know it's not completely true, but this model is so easy to work with that it's kind of better to think of people in that way for science. And even we even use the term rational behavior to mean rational selfish behavior, which is kind of sad. So science understands selfish behavior, and science kind of understands cooperating behavior. I mean, there are models, but they aren't that good. And we obviously, like intuitively and emotionally, we understand why people cooperate because they can achieve bigger things that way. But we don't understand how they put aside their own personal interests. We don't have a model for that. The big thing we're missing is the transition. We know that the cooperating creature evolves from the selfish creature, but we don't know how that happens. And let me be more precise. We know how the process starts and we know how it ends, but there is something in the middle that we don't understand. So I'm going to talk about how the process starts and about how it ends. This is how the process starts. I was saying that this is so difficult to get the cooperation because all of the agents are selfish and they are similar. But in reality, it looks more like this. There is lots of randomness in the behavior of the agents, right? Sometimes this randomness is intentional and sometimes it is unintentional. And it is possible, it is conceivable that because of this randomness, once in a while, there will be two agents that happen to be in a good mood, and the first agent happens to cooperate with the second one, and the second one happens to cooperate back. It is possible, and if cooperation will be built, it's likely to start over there. But the challenge is that we don't know how to take it to the next step, because these agents need not only to cooperate on accident, they also need to sort of understand this is a good thing and that they have to preserve what they've got and grow it and add more people. And sort of not only have cooperation, but reciprocation. And we don't know how to get there. So that was the first part. Now we talk about the third part that we know that we understand, and that's the convergence. And I'm going to show you an experiment. Right? Uh, Wait, let's go back. I'm going to show you an experiment that I did 10 years ago. And in this experiment, there are three populations playing a game of iterated prisoner's dilemma. We've got angels, devils, and tit for tat. Angels always cooperate, devils always defect, and the tit for tat agents play tit for tat. And we're going to see the way that their populations change according to how many points they've gotten. Now, there is no RL here, no reinforcement learning, only evolution. So the groups that grow are the groups that get more points. So let's see how the population evolves. At first, they start as equal, and the angels start dying off. The angels die off because the devils are taking advantage of them and taking points from them. The devils and the tit for tat grow. The devils because they take points from the angels, and the tit for tat because they cooperate within themselves, but also they don't lose points to the devils because they know how to defect defensively. And now that the angel population has gotten so low, it caused the devil population to die because they don't have anyone to take advantage of. And the beautiful thing here is that after the tit for tat has almost gotten over is almost taken over the entire population and has almost killed off all the devils, now the angel population has grown from being like 10% to being around 25%. So that's a nice thing to see. And it's awesome to see the way the tit for tat has gone from one third to three-fourths. It's like as soon as these reciprocating agents, as soon as they hit a critical mass, they take over the entire population, and the cooperation just goes everywhere. So that's beautiful to see. But that only works after there is a critical mass. And the question is, how do we get the middle part? How do we get to that critical mass of reciprocators? And that, to me, is the most fascinating scientific problem I've ever seen. And it is it is such a deep question, both scientifically and spiritually, because this is something that we understand intuitively how this happens. Lots of our art and cinema, our stories, our cultural stories are about the sort of miracle that happens when selfish agents or people who don't really care about each other sort of getting adventure with each other and develop bonds and develop a group that sort of makes that group greater than the sum of its parts. Now we know it happens, and this is fascinating to us, but we don't have a scientific model to explain that. And I think that building a scientific model and using multi-agent reinforcement learning to test it and prove that it works is the most fascinating scientific problem I've ever seen. Uh, I'm taking a huge risk working on this research, and this is why I'm taking the risk. If I can even make a dent in this problem, if I can make any kind of progress towards solving it, it will be an awesome achievement. Let's talk about how I plan to teach agents to reciprocate. And we want to teach the agents tit for tat, which means we want to teach them to change their own behavior for the better against their instincts, to get the other agent to change its behavior to cooperate against its instincts. And this is such a big pill to swallow, and we have to break it down. And other research papers have tried to break it down that way, do the first part and then the second. But I don't believe in that. And I'm thinking I want to break it down that way. This means I want us to have a setup where the agents do listen to each other and do change the behavior based on the behavior of other agents, but not in a situation of a social dilemma. I want them to be flowing with each other and listening to each other and mimicking each other in a win-win situation. And after they've got that going, I want to slowly raise the stakes and introduce a social dilemma. And I think that after getting that communication that was built up in a win-win situation, it might be easier for them to step up and use that in a social dilemma. And let's show a couple of experiments I've done. This is one called Grid Royale. I've done that back in 2020. There isn't any cooperation here. Just we had agents that are seeing food on the world and going for that and eating that. And I put that online. There's a live link there, and I played around with that, getting the agents to eat the food and mostly not crash into each other. And that was interesting. And I also really believe in having demonstrations which are web-based, which make it easier for people to play with interactively, which is something important to me. Um, but after iterating a lot on these experiments and adding new rules, like letting them shoot each other, I saw how difficult it was for me to make that iteration. Every experiment had lots of resistance. So now what I'm working on is a framework that's going to let me make these experiments and iterate on them faster. So that's pretty much where I am right now. Um, this is it. It's all I got for now. If you know of any relevant research that I've missed or you got any insights, please email them to me. If you would like to get updates about the research, please sign up on this mailing list. And thank you for listening to my talk.